we're going to work on graphing using mapping notation. So we're going to graph a wave, but you can technically use this mapping notation to graph any function, as long as it's kind of set up in this form that's easy to view for transformations. Okay, so this is like a small formula for your mapping notation. Okay, mapping notation is where you have your original set of coordinates. So say we're gonna originally graph this. We'd have a coordinate. Let's say, I don't know, it's like 0 and oops, that's not what I want. Let's say it's 0 and 1. Okay, so 0 and 1. And using mapping notation, we can use these values. I put a straight line because 0 will zoom in, but I can use 0 and 1 and put them in to find out where our new coordinates will be. Okay, so what this says is the new x value, that's what that subscript stands for, is equal to the old x value divided by whatever the k is, which is here, plus d. Now, because I've used plus, what that is I have to extract d from here. So because this is a subtraction sign, if this was -5, then the d value would be plus 5, okay? And if this was plus 5 in here, well, then this would be -5. So you have to keep that in mind. The d is the only real tricky part here. The new y value is equal to your a coefficient times the old y value plus whatever the c value is, okay? So you can use that to constantly move points along a page. So first thing we're going to do is graphing cos. Say we know nothing about cos x, okay? Well, one way you can go about graphing if you know nothing about a function is by putting in x values and solving for the y values. So as you can see here, everything's written in degrees, okay? So all my x values are in degrees. So it's usually helpful. We'll start at 0, and then we can kind of extend the pattern. But I'm going to look for when x is 0. And because it's a wave, I purposely chose these x coordinates. We're going 0. We'll use 90, 180, 270, 360. Now, I've chosen those very specifically because I know they're getting this values. But this is an idea of how you can graph a function. You can kind of just put any values for x in and then solve for y. So what that means is if I put cos 0, so let's say cos 0 is equal to 1. Okay, that works out great. My very first coordinate, okay, is 0, 1. So 0, 1. There's our very first coordinate. And we'll kind of go through the pattern here. Cos 90 is equal to 0. Okay, so the next coordinate is 90 and 0, so we go over to 90, we plot our 0. So we're just going to pick a bunch of coordinates, and then once we think we've got our pattern, because this is a wave, so cos 180, and once we think we've got our pattern, we'll continue it. This is going to be -1, 180, -1, 270, do you know what it's going to be?
0.
Yeah, exactly. It's going to be 0, and then 360 is going to be 1 again. So we know that because we're familiar with waves. If you didn't, you can kind of just continue along. So this is a wave function. So what is our 450 going to be? Do you know what that's going to end up?
Okay.
Yeah, it's going to go back down to 0. So this is setting up, and I'm not very good at freehanding this. It should be more of a wave. But it's coming back and forth, right? So 0, which means I can take the pattern backwards. My -90 is going to be here, -180, 270, 360, 450. So it's very symmetrical, actually, along the y-axis. Now, this is y, or I guess I could have called it f at x, but this is for our cos x function, okay? Now, consider this the old x value and the old y value. Let's look for our new x value and our new y value. One thing we could do, we actually need some coordinates. I haven't written out a new function. Let's say our new function is, what was the one they gave you there?
Sine.
Let's use the cos on the other page. You had another one.
Yeah, the other page.
I think it said 2. I can just make it up.
2 cos.
Yeah.
Bracket 2 theta or 2
Theta.
x.
Okay.
Bracket +1.
+1. Great. Okay. The very first thing we need to do in order to figure this out is figure out what our a, k, d, and c values are. So what number represents the a?
2.
2. Very good. So here's our a. What represents the k?
2.
2 again. Good. What about d?
There is none.
There is none. So what number represents d?
0.
That's right. So d is actually equal to 0 here. The reason I didn't write it in is because you could write 2 theta plus 0, but 0 doesn't do anything. Which really leaves us by deduction, c must be the value of 1. Okay. So what that means now is we can now build small little formulas that will constantly solve these. Okay. So I'll rebuild the formula at the bottom of the page here. our new x is equal to our old x over the k value was 2. And the d value is 0, so I can put plus 0, but it's really going to be whatever the coordinate is we're dividing by 2. And the new y value is equal to the a value, which is 2, times our old y value, and plus c, which was positive 1. So plus 1. So we're going to constantly plug these values in to find it. Now, you might have been good enough, or you might already know that these are stretches, so I know that everything's going to be kind of stretched like this. We have horizontal compression, so it's going to happen like twice as fast, and the whole thing's going to move up 1 unit. That's the general idea, but sometimes we're not really strong with that. So using coordinates works out fine. We're going to plug each of the coordinates in just the same way we did before. These 1, 2, 3, 4, 5. These are 5 major ones. And from those 5 major ones, we'll probably be able to find out the pattern again. So the very first one is 0, 1. So our new x is equal to our old x, and our old x was 0, 1. So our old x is 0 divided by 2. We don't need to put plus 0. So our new x is still 0. That's great. And our new y is equal to 2 times 1 plus 1. So that is 2 times 1 is 2 plus 1 is 3. So our new coordinate is 0, 3. Okay? So this original coordinate has now transferred over to 0, 3. So we'll plot it 0, 3. Okay, so much higher than before. And we're going to run through this with each of these. So I'm going to try to go somewhat quickly. The new one, our next new x was 90. Our new coordinate is 90, 0. Okay? So 90 divided by 2, x new is 45. And y new is equal to 2 times 0 plus 1. 2 times 0 is 0 plus 1 is 1. So our new coordinate is 45, 1. Okay? So that's a lot more condensed from where we were before. This is 90. That means halfway would be 45. And here is our 1 value. Our next one is 80, or 180 and negative 1. So 180, negative 1. We'll just continue putting through the formula. Our new x is equal to 180 divide 2, which is 90. And our new y is equal to 2 times negative 1 plus 1, which is negative 2 plus 1, which is negative 1. So 90, negative 1 is our next one. 90, negative 1. Coordinate 90, negative 1 is right about there. 270 and 360 are our last ones. 270 is at 0. Okay. So x new is 270 divided 2 is going to be 135. And then I already know that 0 is going to be 1. My new y is going to be 1. So 135, 1. I know I'm doing that kind of fast, but you could use a calculator to kind of do it, right? 135 is right in between here. It's at the value of 1. So we're already starting to see a pattern if this is wave-like. We can go on the assumption that our next coordinate is probably going to be 180 and that value of 3. And I'm going to tell you it is. So if you were to plug that all the way through, you would end up with 180 and 3. So that's where each of these corresponding points have now transferred to. So if we I'll try to freehand it in. Okay. Remember the old period, okay, of this function occurred in 360 degrees. Mm-hmm. This one now occurs in 180. So it's been compressed by a factor of 2. It's much longer, so it's been stretched by a factor of 2. And the equation of the axis has been shifted up 1 unit, which is exactly what we had in a k, and a c value. So we can kind of just continue that pattern if we want. You could do this for every point, but that becomes really tedious. So knowing how to stretch things is really helpful. We know the next point will be halfway between, back at 1. 270 will be here, halfway between, and then 360 up here again. And we're ending up with that very similar pattern. Comes back down there. Ooh, I'm actually pretty good freehanding it this way. And then exact same thing, same pattern. 180. Now I'm just showing off. Let's see if I can get into that. And I think I got that right. There you go. Okay, so it has that idea of being stretched vertically, compressed horizontally, and shifted up 1 unit. And just to make sure, here's our cosec's. there's our wave. This is in radians, so I'll quickly change it to degrees, which means I gotta go from negative 450. Oh no, that's the y-axis. Negative 5 to positive 5 is good. And negative 450 to positive 450. There we go. And we said our new function was 2 cos bracket. Now they got to use x to actually graph it like this. Plus 1, we wouldn't use theta, but there it is. It's the exact same thing we drew on the other page. We just kind of used our mapping notation for